CSIS 2430 is filmed before a live studio audience.
Now that we have a basic understanding of the foundation of propositional logic, let's take a look at why we care about all this stuff. Why does it matter? So the big question of the day again is why? There's lots of different reasons why. Mathematical arguments, which we'll talk a little bit more about that in a minute. Disambiguating language, which kind of ties in with the mathematical arguments. Then there's things dealing with hardware and software specifications. We'll look at some examples of that today. Computer circuits, believe it or not, we can use propositional logic to help design, and not only design, but improve computer circuits. It also can help us in writing code, helping our code be more logical and more clear and more concise. Not only that, but it can also help us analyze our code, which again can get back to making more clear, more concise, and more precise code. You can use it to solve logic puzzles, and believe it or not, we're going to take a look at it and an example of that today. And you can also use it to write or code up a proof, a mathematical proof, and a whole bunch of other stuff. So let's start by breaking down some of the topics we'll specifically get into that sort of relate back to those things we just looked at there. The first thing we're going to look at is how to translate English into logic. And that gets back to this idea of creating mathematical arguments, right? If you start off with just an English sentence, English language is very ambiguous. Speak to anybody who has learned English as their second or not their first language, and you will see that it's a really weird and tricky language to learn and to wrap your head around, and there's so much ambiguity in the language. So if you can convert a sentence or an idea from English or whatever language into math, then it's clear and it's pure and there's less error for ambiguity. We're going to look at how this can apply to system specifications, right? With a system specification, you can say it verbally, but until you express it mathematically, there's room for some ambiguity there. And as I mentioned a minute ago, we're going to look at some logic puzzles today, and we're going to do a few practice exercises. So let's start off with this idea of translating English into a sentence. And why would we even want to do that? As I mentioned a moment ago, the language is pretty ambiguous. So this can help remove the ambiguity. That's one of the reasons we'd want to translate a sentence into math. Secondly, once we've translated it, we can properly analyze the truth value of the statement. Again, this is tying into this whole ambiguity thing. Then, once we've converted this into a mathematical statement, we can manipulate it using the rules of inference, which we'll learn about in chapter 1.6. We will get to that another day. But those rules of inference, they're all logical equivalencies or things that you can infer from. If we know this thing is true and that thing is true, then we can infer this third thing to be true. Without converting the sentence to math, you can't do that. So it helps us to be able to use a mathematical version of an English sentence that we can then take down a path to see if it's true or not. And of course, all of that leads to proofs, right? That's what proofs are all about. You have statement A, statement B, statement C, therefore statement D must be true, right? Well, without converting these statements A, B, C into math, you can't prove that D is going to mathematically be true unless you convert them. So it removes the ambiguity, turns it into a mathematical formula, then you can apply these rules of inference we're going to learn about another day, and that helps us do proofs and helps us prove the truth of things. So here's an example here. Translate this sentence into a logical expression. Butthead can access the internet from campus only if he is a computer science major or he is not a freshman. Now, before we answer this question, the real important question is, do you know who Butthead is? If you do not, then you need to stop watching this video right now and go find out. We're going to meet his compadre here in just a minute. So, Butthead can access the internet from campus only if he is a computer science major or he's not a freshman. So how can we represent this using the techniques we learned about the basics of propositional logic, assigning variables and using the conjunction, disjunction, and all these things? Well, here's one way you could do it, like this. P, right? That's it. You're done. let P be the statement that Butthead can access the internet from campus only if he's a computer science major or he's not a freshman. That's a completely valid way to do that. P is that statement to the end. Now, it's a little silly because you can't really do much with that, so we want to express it in a more mathematical way using the techniques we've learned about earlier. So let's take a look at different pieces of the sentence and see if we can make a little bit more of a mathematical representation of this. So let's start off by letting A denote that Butthead can access the internet from campus. Right? That's basically the first part of our sentence here, right? That Butthead can access the internet from campus. Okay, so that's part one. Next up, let C denote that Butthead is a CS major. So he is a computer science major. All right, and then the last piece of it, let F denote that he is a freshman. Now notice this says he is a freshman, this says he is not a freshman. Okay, what's going on there is, the best way I can explain this, or a good way, is the following statement from Groucho Marx. Groucho Marx once said, "I cannot say that I do not disagree with you." Right? What the heck does that mean, right? And I'm not going to answer that because you actually have a homework assignment where it asks you that very question. But I cannot say that I do not disagree with you. The problem with that sentence is there's way too many negatives in there, and it's hard to translate. So the best way to handle these situations is, if you're dealing with a negative in the original sentence here like this, and you're trying to convert this into a mathematical expression, remove all the negatives in your initial variables, right? So as we've covered before, we just use variables, typically P, Q, R, S, and so forth, to represent propositions, but it doesn't have to be those things, right? We're using A, C, and F here. And so we're going to say F is that he is a freshman. Now, if I want to represent he is not a freshman, of course, we can say not F, right? And so we'll need to do that in our equation. But let's see if we can represent this now as an equation using these three variables and our original sentence. So ignore this whole sort of silly thing here, okay? So pause the video for just a second and see if you can come up with a formula that mathematically represents that sentence. Okay, let's take a look at the answer to this. This one states A, therefore, C or not F. Okay, what does that mean? Whenever we have the conditional arrow, then the thing right before it we always say as if. So this is saying if A, therefore C or not F. Let's put that into English terms. If A, which means if Butthead can access the internet, therefore he is a CS major, C, or he is not a freshman. So does that line up with our sentence? Butthead can access the internet from campus only if he is a CS major or he is not a freshman. So you might ask yourself, what about this? Why doesn't this work? This is saying if he is a CS major or he is not a freshman, therefore he can access the internet. That sounds true, right? Doesn't that seem like that's right? The truth is it's not. And we're going to see it in a truth table in just a minute to prove it, but let's just look at it from a logic perspective. Why is that not true? One way I like to think about this is this idea, when I was a little kid, I made a fort in my backyard and no girls allowed, right? It was only boys. So if you were in the club, you're a boy. But just because you're a boy doesn't mean you're in the club. Otherwise, every single boy on the entire planet would be in my club, which is kind of silly. So this is kind of the same idea. If you're in the club, therefore you are a boy. But just because you're a boy doesn't mean you're in the club, right? That's not a true statement. This bottom one here would not be true. So if we kind of see A as being in the club and C or not F being a boy, then that would say if you're in the club, you're a boy. Well, by that same logic, then we're claiming here that if you're a boy, therefore you're in the club, and that's silly. That's not the case. So you can see those are two different things. Now, how does that tie into this whole campus and not a freshman thing? Is it possible to be a CS major or not a freshman, but you still are not allowed access to the internet? Is that possible? And of course it's possible, right? You don't have a computer. Now it says you can access it, right? Well, that's one of these ambiguous things. What does can access it mean? Have the ability, have the knowledge, have the technology, have the proximity to the network. There's lots of different things that could mean. And so this is the kind of thing where we need to get some clarity on it. But we can easily see that just because you are these things does not guarantee that you are allowed access. However, the opposite is definitely true. If you have the access, you must have at least those two things. Okay? And let's look at them logically in a truth table. They are different things. So take a brief minute and look at the truth table here. Make sure that we agree that it's set up properly. We have every single possible scenario of A, C, and F. And then we also make sure that we have not F right here. Then next up we have C or not F. And then here we have the first one right here. And here is the second one right below it. And you'll notice that they're not always the same truth value every time. If these things were the same as each other, then each row, these would be the same every time. So in that case, they are the same. In that case, they are the same. But here, look, they're different, right? So let's erase all my scribbles here. If these two equations, this one and this one, were the same, they logically had the same propositional value, then whatever mixture you give the truth values here would result in the same thing in both of these formulas. But because in this particular case, when you have a, sorry, I just meant those three there. When you have a true, false, true, you get a false there and a true there. Well, that's not the same behavior as each other. This one behaves differently from that one. So they are not the same. So this truth table is sort of a little mini proof that they're not the same. But hopefully you, using my little silly boys club analogy, you can sort of see logically why they're not the same either. Okay? All right, let's try another one. Translate this sentence into a logical expression. This is Butthead's buddy, Beavis and Butthead. Again, if you don't know who these guys are, stop watching this video and go find out.
That was cool.
Okay. Beavis cannot ride the roller coaster if he is under 4 feet tall, unless he is older than 16. Okay, this is going to be a weird one. Okay? And again, we could do the silly thing of saying, let P be the statement that Beavis cannot ride the roller coaster, ... right? But we're going to take the more useful approach and let's assign some variables here. So let's start off with Q, stating Beavis can ride the roller coaster. Remember what we talked about a minute ago, where we don't want to have all these negatives here. So we're going to start with the positive statement, and then we're going to negate it in our formula if we need to. Like we did with the freshman thing, we negated it as we needed to, okay? So that's the first variable. Then R is Beavis is under 4 feet tall. Now this is a little bit weird here, right? He is under 4 feet tall, okay? Now that says under 4 feet table. That should say under 4 feet tall. Sorry about that. I'll edit that later. But that he is under 4 feet, all right? I was just going to go with that, okay? So Beavis is under 4 feet tall. Now I could have made R be the statement that Beavis is over 4 feet tall, right? And the formula would end up being different if we did that, and that's a valid way to do it because it's not really negative or positive, right? So just sort of pick one. I just went with what was already in the equation here. And then the last one here, he is older than 16, right? So let's let S denote that Beavis is older than 16. Again, we could have chosen S to denote that he is younger than 16, but I figured since it sort of matches what's in our formula here, this works, okay? By the way, these two examples, the one we just did and this one here, they're both in your book. They're just not using Beavis and Butthead. Okay, that's just out of my sick, twisted mind here. Okay, but these are in your book. Okay, so let's see if we can formulate this, and I want you to give it a shot. Take a minute, pause the video, and see if you can pull it off. I know you can. All right, let's take a look at the answer here. Now, this is the one I told you a minute ago that we're going to look at two possible answers. Are there more than two? Yeah, I'm sure there are plenty. But we're going to start with these two. Let's first make sure that this one makes sense, then we'll look at the second one. We'll talk about why/how they're the same. First, this one. This states R and not S, therefore not Q. Or if R and not S, therefore not Q. What does that mean? If Beavis is under 4 feet tall and Beavis is not older than 16, which means he's 16 or younger, therefore Beavis cannot ride the roller coaster. That's what that sentence claims based on those variables here and this equation here. Okay, so take a look at that, make sure that makes some sense, and let's see if that applies to what our original statement is. Beavis cannot ride the roller coaster if he's under 4 feet unless he's older than 16. So think about the rules here. What allows you to ride the roller coaster, or what disallows you from riding the roller coaster? Well, you can't ride it if you're under 4 feet. Okay, so here we're saying you can't ride it. That's what Q is. You can't ride it. Well, what led to that condition? Well, what led to that is you are under 4 feet or you're not 16 or older. Okay, so this makes sense from a logic perspective. You are under 4 feet and you're not older than 16, therefore you cannot ride it. If one of these were true, right? If both of these weren't the way they are, right? If R were false or not S were false or something like that, then you'd be able to write it, right? But the problem is you're not allowed to write it if R is true and if not S is true. Okay, so hopefully that makes some sense. Let's take a look at the second equation that maybe some of you got this one. This is the second equation. Now this is saying Beavis can ride the roller coaster, therefore he must be either not under 4 feet, in other words, taller than 4 feet, 4 feet or taller, or he's older than 16. Remember the rule. What prevents you from riding the roller coaster? Two things, your age and your height, right? If your age is the wrong age, or you're too young, or you're too short, then you cannot ride it. Well, in this case, you are too young because you're under 4 feet, and you're too short because you're under 4 feet, and you're too young because you're not 16. Therefore, you cannot ride. Well, in this case, you can ride, which means that you're not too short or you're not too young, which is what's going on here. You're not too short or you're not too young. Okay? Or you're old enough is a better way to say that, right? So this, again, this last one here, you can ride, therefore you're not too short, right? You're not R, because R means you're too short, or you are old enough, right? Because S means you're 16 years or older. Now, how are those the same thing? I think if we talk through them like we just did, it makes sense just in our brains sort of logically, but let's look at the actual raw logic of it, right? So let's switch over here to the chalkboard, if you will. Okay, let's shrink it up just a hair. This first one here at the top there, that's our first equation, and that's R and not S, therefore not Q. Again, if we go back here, R and not S, therefore not Q. The second one there, Q, therefore not R or S, right? Notice here that we can just ignore everything else. We don't have to worry about what the words are, what they mean. We just have these formulas here. So the question is, how in the world do you go from this to this? And part of it you've already been exposed to. The other half of it you have not been exposed to yet, so you're going to have to kind of push the I believe button, which is right in the center of your forehead, in case you're wondering where that's at. Okay, so you have to just sort of take me on faith. But the first part you already know. The first part is the contraposition, right? If you remember, the contrapositive of something, P, therefore Q, the contrapositive is not Q, therefore not P. Okay, so if we apply that, let's just erase all this stuff here. So let's take this right here, the top equation, and see if we can use the contrapositive on it, all right? So if we do the contrapositive, remember the P and the Q switch places, and then you negate them both, right? So the Q here is going to go on the left of the arrow, and then the R and not S is going to go on the right. So you end up with this thing here, the thing that was on the right is now on the left. Therefore, the thing on the left is now on the right. Right? So R and not S. Now remember, you also negate them both, like so. Okay? Now, we haven't learned this yet officially. We will be getting to that another time. But what do you suppose happens when you have not something, right? It's just like in math. a negative, -1 is a positive one, right? So not Q is just simply Q. And then here's the part where you're really going to have to push that I believe button, which is what's called the Morgan's Law, okay? And we are going to learn about that. But for right now, just take me on faith. If you apply de Morgan's Law to this R and not S, you will end up with the following. You'll end up with not R or not S. That's what you'll end up with if you apply de Morgan's Law. Again, you got a double negative there, so when all is said and done here, you end up with a Q, therefore not R or S. And if you'll look, that is our second yellow equation right there. See if I can shrink this a little bit. Right there. So this right here, that's exactly what we have right here. So we applied the contrapositive, then we applied de Morgan's Law, right? And remember, the contrapositive and the original are identical logically, right? We learned that on the previous video, okay? So we applied the contrapositive, and then the next thing we did is we applied something you haven't learned about, which is the double negation law and de Morgan's Law. But between those two things and the contrapositive, we've just actually done a sort of mini proof here that this and this are the same thing. Now, if that went over your head a little bit, don't panic too much. Wait till we learn about de Morgan's Law, and then maybe come back and watch this part again now that once you understand de Morgan's Law. But once you see that, it'll make perfect sense that those two are logically the same thing. Okay, so I think we have enough proof / evidence here that those two things are the same thing. Let's take a look at a different reason why we care now about translating English sentences into math. System specifications. We can state a sentence in English saying, this is what the system does, but it can be ambiguous. We've mentioned this a couple times now. So here's an example of a couple of funny sort of ambiguous, or not sort of, they're definitely ambiguous statements that are kind of funny. These are both ones that a guy I used to work with years ago named Jack Mahoney told me about. I just want to make sure if somehow he ever sees this video that he gets the credit for these sentences. But the first one is this. Next to this tree, I love my children the most. Now I want you to just pause for a minute and think what that could possibly mean. There's more than one interpretation to what that could mean. Maybe this is a tree that he just loves, whoever's speaking here, just loves more than anything, right? Other than this tree, I love my children the most. It could mean that. I think we'd all agree that it could mean that. Next to this tree, I love my children the most. But it could also mean that when he's standing in the proximity of the tree, that's when he feels the most love towards his children, right? Which would be a more descriptive way to say that if that's what he meant. So next to this tree, I love my children the most. When I stand near this tree, I love my children more than when I'm not standing near the tree, okay? So that could be either way. If we wanted to convert that into a mathematical sentence or a mathematical formula, we'd have to get a little bit more specific, and we need to speak to whoever said this sentence, right? The second one is a little bit more dangerous, though. You can never put too much water in the reactor coolant system. Now, what does that mean? Does that mean it's not possible, right? The reactor coolant system, you can't put too much water there. No matter what you do, it's never going to be too much. Could mean that. Or it could mean you can never put too much water in there. Don't ever do that. That's a bad thing, right? Which one does it mean? If you think it means the first one, then you might put too much water in there because you thought that there was no such thing as too much water. So again, silly questions or silly statements to prove the ambiguity of the English language, okay? So, what can we do about this, right? Well, the problem with this is we write, as humans, we write instructions for a system or software given in, as an example, English. And speaking as a guy who has worked with other humans to create software for these humans who don't speak in this, and they don't speak unambiguously, they speak very ambiguously. They hated that I would ask them questions that were very specific. I would say, look, I know that in your brain you know what it's supposed to do, but we have to transfer that information to my brain so I could transfer it to code, right? And so the problem becomes whenever they say a statement, next to this tree, I love my children the most. And I say to them, what do you mean? And they go, what do you mean? What do I mean? I mean that next to this tree, I love my children the most. And then I'll say to them, well, what does that mean to you? Then somebody else in the room pipes up and says, well, he means this. And my response would be something like, look, I know that that's what you think he means. I want to know what he thinks he means, right? So I know it's a silly thing, but that kind of question, when you're talking about a software system, the last thing you want to do is build a system that you thought was what they wanted, and turns out it wasn't. So you have to be very specific in your language, and you have to be unambiguous. And as a software developer, I got this reputation of, I don't know if arguing is the right thing, but questioning everything to make sure I fully understood it. And that comes from this background here in logic and critical thinking and propositional, calculus is what Aristotle called it, propositional calculus, right? It comes from this background because without that clarity, you can write some bad code, and that's no good. Okay, so sorry, I'll get off the soapbox. Sorry about that. Okay, again, the engineer has to translate it into precise, unambiguous specifications, right? Especially if the engineer's not going to build it, they're just going to design it. Then we got to work with somebody else that's going to build what the engineer writes out, and it has to be unambiguous. And as I've mentioned when I was on my soapbox a minute ago, right, this is very important when it comes to system development. So let's take a look at some examples of how this might play out. So we're going to express the following using the logical connectives, and again, those are the and, the or, the not, those types of things, and let's see how this plays out, okay? So the following are system specifications for whatever particular system we're talking about here, right? The automated reply cannot be sent when the file system is full. This is a statement that has to be true about this email system we're building or whatever it is here, right? So this is a requirement from the powers that be. The automated reply cannot be sent when the system is full. So now, how do we represent this in propositional logic using logical connectives? Well, we could do the silly thing, which is let P be the whole statement, right? But we want to break it down, and then eventually in a few minutes here, we're going to test something like this to see if the statements are even consistent, if they can all exist, right? Right now, we've only got one statement. The automated reply cannot be sent when the system is full. So let P denote the automated reply cannot be or can be sent, right? Okay, there's that little negation removal thing, right? Let's take a look at the next variable, Q, the system is full, right? Between those two, I think we can see pretty easily how to convert this into a propositional statement. So take a minute, pause the video, see if you can crack it real quick, and then come right back. All right, so let's take a look here. Q, therefore not P, right? The file system is full, so if the file system is full, therefore you cannot send the reply. The reply cannot be sent, which is exactly what this sentence says right here. So this is how we would represent this as an equation, right? Now, why would we need to do that? Well, what if we had multiple statements here? We had this one and we had a couple more, and what if they were conflicting, right? So let's take a look at multiple statements here in just a moment and see if we convert them into a mathematical statement and apply our logic and critical thinking skills to it, maybe a truth table if we need to see if all of the requirements or the specifications can even physically possibly be true at the same time. Okay, so let's take a look. So we call this idea consistency, right? So we want to make sure that to keep things consistent, we avoid conflicting requirements, right? So we could be given one requirement, and then we're given a second requirement, and it turns out those two contradict each other. Well, sometimes in the ambiguities of the English language, that may get overlooked. So we have to be careful. So this will prevent contradictions by making sure things are consistent. And all this simply means is that all of the specs can't be satisfied. If they can't all be satisfied, then the system is not consistent, and therefore it's either been explained to us incorrectly, we understood it incorrectly, or it's actually just wrong. And so we have to figure out which one that is and fix it, right? So let's take a look at an example here, and we're going to determine whether these specs are consistent or not. So the first one, the diagnostic message is stored in the buffer or it is retransmitted. What does this mean? What system are we building here? I don't know, right? But we're just going to use this as a requirement that was given to us as the engineer, right? So the diagnostic message is stored in the buffer or it's retransmitted, okay? Next up, we have this. The diagnostic message is not stored in the buffer. And then we have this one. If the diagnostic message is stored in the buffer, then it is retransmitted. So what we need to find out here is this. All three of those statements, can they be true at the same time? Can a system have all three of those things and there's no conflict, all right? How do we do that? Well, we convert it into math like we did a minute ago, or a propositional condition or a propositional statement, and then we're going to look at some sort of logic our way through it, right? So let's start here. We'll let P denote the diagnostic message is not stored in the buffer, or excuse me, is stored in the buffer. I do that all the time where I forget we took out the negation right there, right? Okay, so that's P. Then let Q be the diagnostic message is retransmitted. Okay, so that's right there, it's retransmitted. And if we apply those, we get these formulas right here. Okay, we have P or Q. So let's clear off all these little lines here. We have P or Q, right? The diagnostic message is stored in the buffer, or Q, it is retransmitted. Okay, so that's the first part. We converted that one to an equation. Second part, we converted that second bullet point to an equation, which is saying not P, which is the diagnostic message is stored in the buffer. We're saying not that, which is what's going on here. And then the last one says, if the diagnostic message is stored in the buffer, therefore it is retransmitted. And that's what P therefore Q states. So we've converted it, but now what? Is it consistent? Well, let's find out. Okay, so we can ignore all of the words now and just look at the formula, and that's it. So what we want to do is find truth values that make all three of these things true. Because if they can't all three be true, then we have an error in our system, the way it's supposed to work. It can't actually work that way, okay? So what can we do about this? This is a small enough one that we could probably throw it in a truth table, but it's also kind of a small enough one that we can just sort of think our way through it. So let's do that, okay? First up, we have these three separate statements, right? And remember, these were the three bullet points, and we converted them to these formulas, and they need to all be true. Well, in order for that middle one there to be true, right? In order for this guy to be true, that has to be true, which essentially is just the same thing. I just got parentheses on it, right? Well, not P must be true in order to make that true. Okay, easy enough. So let's look at the consequences of not P being true. What are the consequences of that? Well, that means P is false, right? I think we all agree with that. That means P is false, which means this dude right here is false. P is false. Okay, if P is false, what must occur for that whole thing to be true? Well, that's Q must be true, right? In order for this to be true, because we know that P is false, well, then Q has to be true. Because if they're both false, if that's false and that's false, then the whole thing's false, okay? Okay, so we now know that this P here is false. We know that this Q must be true. Okay, if this is true, knowing the way conditionals work, in order for the whole thing to be true, then P can be false or P can be true in the event that Q happens to be false. But we know, excuse me, I said that backwards. Let's try that again. Okay, we know that Q is true. Okay, if Q is true, then P doesn't matter. It could be true or false. Well, we know P is false. So if we have a false, therefore true, then that whole thing evaluates to true. Okay, hopefully that made some sense there. And so that means that if this is true, then all these other ones will be true. They all follow. Okay, therefore, again, that makes that true, and therefore the specs are consistent, right? So all of those things can exist. We're going to look at another one that it's going to end up not being consistent, but I want to make sure we understand this process here. So hopefully that makes some sense. Okay, let's take a look at this one here. Determine whether these specs are consistent. Sounds familiar? Message number one, or statement number one. The diagnostic message is stored in the buffer or it's retransmitted, just like the one we just did, but we're going to add something to it. Next one, the diagnostic message is not in the buffer. If the message is in the buffer, then it's retransmitted. And then our last one here, the message is not retransmitted. So now we have a fourth component here. We're going to go through the same process like we did a minute ago and convert these into equations, right? We'll let P be this statement here. We'll let Q be this statement here. And then we get these formulas. So take a minute, make sure, if you need to pause the video, that's fine. Make sure that you agree with those statements, those blue equations there, that they actually match based on these variables here, that they match the sentence they're next to, okay? If we're at that point, we're going to go to the next slide here, which gets rid of all the words and just shows the four equations. So we need to make sure that all three of those statements are true, okay? And so in order for these simple ones here to be true, we just have to say that they're true, right? Which is going to make P and Q not true, okay? So let's just take it one piece at a time. Not P must be true in order to make not P true, right? That's kind of like, duh, Jeff, we get it, right? So I think we're good there, okay? Well, that means P is false, just like we did a minute ago. Okay, so far so good. Now, not Q must also be true in order to make not Q true. That's kind of what I said a moment ago, right? These two guys right here have to be true, okay? Therefore, Q must be false, all right? Now, you can already see a problem right here. If Q is false and P is false, what does that make this? That's false or false, right? P being false or Q being false. Okay, can that still be true? Well, yeah, one of them being false can be true, but not both of them. And in this case, both of them are false. So that means that this whole thing evaluates to false, which means that this is true, this is true, and this can even be true, right? Because we get a false, therefore false, which will evaluate to true. Okay, so that's all good, but this one right here is false. Okay, that is a problem. It's no good. Therefore, right there. Okay, that's not good. Because of that, that means that these specs are not consistent. All four of those statements cannot be true at the same time. And if they need to be true, if the requirement is that they're supposed to be true, well, we misunderstood it, it was explained to us incorrectly, or it's actually just wrong and we have to go back to the drawing board. So hopefully you can see how this propositional logic stuff can be very important when it comes to system design, okay? The whole thing is all about disambiguating, is that a word? The English language, converting it into math so you can do proofs, which we will look at another time, and we sort of kind of did one a minute ago with the roller coaster thing where I showed you the two versions of the formula. But that aside, it's good for proofs, bigger proofs, and for this system specs thing and some other things that we're going to look at in the future. But for now, let's just look at something that's a little bit more fun. Why study logic puzzles? It's a great question, right? And we often see these mathematicians. In fact, we're going to be talking about a specific one who I've actually seen on the Tonight Show with Johnny Carson. And he's just this total math nerd guy. And he talks about these funny, silly puzzles. And people ask the question, why do you bother? If any of you are a fan of the YouTube channel Number File, they often talk about these fun little mathematical weird things that they solved. And you may ask, well, why the heck would you do that? Okay, so it's a good question. Well, one of the things that's interesting about logic puzzles is it helps us work with the rules of logic. We're actually going to use some of the rules of logic, which you haven't learned them yet, right? I keep doing that to you. You haven't learned them yet. You're going to learn them in a few days or whatever, but we're going to kind of apply some of them so you can at least get a taste of what's to come. But it helps you practice with the logic rules, okay? It's also a really good way to make sure your critical thinking skills are sharp so you can test programs that are designed to perform logical reasoning, right? So if you have some sort of, if you're old enough to remember the old choose your own adventure games back in the day, the, Zork and those kind of things, the text-based games, there's a lot of branching logic, right? And if this event happens or the user says this, then you're going to go this way and you're going to go on this adventure, you're going to pick this thing up or look at this thing. So that's a game, but there's lots of other applications for that where you have branching logic, right? It's the if statements and the switch statements that we love when we write our code. Okay, so this helps us to be better at those kinds of things. It's also just fun, right? Why not? It's fun. When I was a kid, I had this really good book called Perplexing Puzzles and Tantalizing Teasers. And I read it and I loved it and had these crazy weird logic puzzles in it. And what I didn't know at the time, it was actually written by Martin Gardner. Years and years later, as I got more into math and magic, I think I mentioned in my bio that I'm a magician, and I got more into this, I found out that Martin Gardner is also a very well-known math magician, a mathematical magician and just a magician in general, but a recreational mathematician as well. And I loved his work as a little kid and didn't even know it. And I recently found another copy of that book, and it's just a great, fun book with some fun puzzles in it. So it can just be fun. Why not? It's okay. So this guy, he's the guy I was talking about a minute ago, Ramus Mullion. When I first saw him, I think it was on The Tonight Show with Johnny Carson, but he grew up in Queens. He actually also a magician. You see a pattern here. And he paid for college with magic, right? So there's lots of different little things about him. I think there's even a little bit of a bio about him in the book. But here's some of his books. I'll just quickly show you a few of them. I think this one right here, The Lady or the Tiger, was the one of the puzzles he was promoting, or one of the books he was promoting on the Johnny Carson show. If you like chess, this is a really good book here, The Mysteries of Sherlock Holmes. The Chess Mysteries of Sherlock Holmes. What those are, they're not chess puzzles per se. They're not the typical, okay, what's the next move, or what's the best move for black to move or white to move or whatever. It's not those kind of things. They're situations where the board looks a certain way with the pieces in a certain place, and the question is, how did they get there? Kind of interesting. So if you like chess, those might be fun for you. But he's got lots of books here, so feel free to go pick some up here if you like them. What's this? Satan, Cantor, and Infinity. That sounds interesting. I don't know what that's all about. This is the next one, Alice in Puzzle Land. That's the next one on my list to buy. Anyway, take a look at his books, though. There's some fascinating stuff in there. Okay? So here's a classic one, and I believe this is actually one of his puzzles. It's the Where is the Treasure puzzle. And we're going to use some basic logic ideas to help solve this. Okay? So you just rescued the king's daughter from pirates, right? And the king says that one of these trunks contains the treasure. Choose wisely. And they're labeled, as you can see here. This trunk is empty. Number 2 says this trunk is empty. But then number 3 says the treasure is in trunk number 2, which is kind of weird because number 2 says it's empty, right? The queen tells you, and she always speaks the truth, that exactly 2 of them are inscribed falsely and 1 of them is true. So how would we even approach something like this, right? We have these labels on them that say one thing, and then the third label contradicts one of the other ones, but the queen says one of those labels is correct. So how do we figure it out? Well, we can use propositional logic, believe it or not. We're also going to use some rules and laws we haven't quite learned yet, but that's okay. We're just sort of looking ahead a little bit to get a taste of how this might play out. Okay, so I'm going to move those treasure chests over there, and I've sort of abbreviated the messages there just so we remember. The first 2 are labeled as being empty, and then the third one says the treasure's in number 2. Okay, how do we do this? We're going to use PI here, right? Let PI denote the treasure is in trunk number I, and just like we're doing a loop here, right? For I is 1 through 1, 2, 3. All right, so this can help us out here. And then these, if we use that, then these are the inscriptions here, right? Not P1, right? Because we're saying that PI or P1 and P2 and P3, right, are the statements that the treasure is in trunk 1 for P1, or the treasure is in trunk 2 for P2. And then the third one actually says that P2 is true, right? So the first statement, this being empty, is saying not P1. The treasure is not in 1, right? The second one is saying the treasure is not in 2. I'm just reciting the labels or restating the labels here using a proposition, right? And then the last one says that the treasure is in trunk 2, right? P2. That's what that proposition is called. So that's what those statements are. We're saying not P1, not P2, and P2. So already there's obviously a contradiction here, right? You can't be not P2 and P2. But that's why the Queen told us, well, one of them is correct. So if we start here, right? It's kind of a weird place to start, but this gets us somewhere, right? Now what do? This is where it gets crazy now, okay? So follow me here. It's not as bad as it looks, though. Okay, take a look. This is what the Queen said, that exactly one of the statements is true. Exactly one of these 3 is true, and the other 2 are false, okay? So, in other words, if we look, just start here, this first one. Not P1, so it's not in the first trunk, and it's not in the second trunk, and then it's not in the second trunk, right? So this is saying not in the second trunk. So she's claiming that one of the statements is true, which means the other 2 are false. So in this particular one, she's claiming this statement is true. That's why we have this. So if those are true, then that's false and that's false. What do those 2 things being false look like? They look like not that, so not P, and then not that, so not P2. Okay? So she's saying that it's either that is the case or this is the case, right? In this particular case, she's claiming that the second statement is true, which means this is false and this is false. Okay, well, if this is false, then you get not that, which is not P1. And then this is the one she's claiming might be true. And then if this is false, then you get not P2. Okay, again, she's claiming that one of them is correct. Well, all we're doing with this weird blue equation here is saying what one of them being correct, what are all the possibilities of that, right? There's only 3 chests, so you can just do all the possibilities. If we had more than 3 chests, it might get a little bit more unwieldy, but this isn't too bad. So either that's the true one and those are false, or that's the true one and those are false, or finally, the last one here, that's the true one and these 2 are false. So if this is the true one, then that's true, and that's false and that's false. Well, that's not that, and that's not P2 and not P1, right? So all we did was took what the King told us, that the first 2 are empty, but the third one claims the treasures in the second one. Then we took what the Queen said, which is, well, one of them is right and the other 2 are definitely wrong. Exactly one is right and exactly 2 are wrong. Okay, well, that means it's either that scenario or that scenario or that scenario. So I want you to pause right there before we go any further and make sure that's processing, right? That's a lot and it's weird, okay? For sure, I'll be the first to tell you. Make sure that that makes some sense, okay? Once that works, then we'll move on to the next part. Okay, hopefully our brains are all in check and we're ready for the next piece. Now, what the next thing's going to do is we're going to apply, essentially, algebraically reduce things, right? And I mean, we're going to get rid of all these double negatives that are all over the place here, right? And little things like, you know, of the same thing and the same thing, so you can just get rid of one of them, right? So we're going to learn about the rules that allow you to do that later, but just for now, you have to kind of push that I believe button again, all right? But let's do some reduction here, okay? Starting off here, I got rid of all the double negatives. That's all I've done, okay? So this here becomes this, and then this becomes this, and that becomes that, okay? That's all I've done, just got rid of the double negatives. I think we can all easily accept that one. Even though we haven't officially learned that rule, it's pretty much makes some sense. Let's look at the next one though. Now this one's weird. Where does F come from? Well, we still have something or something or something, right? We still have these three things separated by two ors. It's just that this thing we've replaced with an F, which means false, right? So why did we do that? Well, because I'm claiming that not P1 is true and P2 is true. So far that's possible, but and not P2 is true. Well, how can P2 be true and not P2 be true? That's impossible. So they both can't be true at the same time. So one of these is true and one of these is false, which means that not all three of them are true. If not all three of them are true, then the whole thing evaluates to false. That's where this comes from, okay? Notice the second one here went from this to this. How did that happen? Well, again, if I have this and this, that's just the same thing twice, right? If I say that P is true, I could also say P and P and P and P and P are true. But it's the same thing as just P, right? And then the same thing's happening with the last formula here. We got P2 in there twice. So we've removed the duplicates, we've evaluated the one that's clearly false, and we're left with this. Okay, now what? Well, let's see if we can go any further, okay? In this event, we know this is out of the equation, right? It's false, we don't need it. We're trying to find what's true. We've already eliminated that this first scenario cannot even happen. Okay, so it's gone. So now we're just simply left with either the middle scenario, which is what we originally started with, this guy or that guy, right? One of those are going to be true, okay? Well, which one is it? Don't know, not yet. Let's find out. So now, where did this come from, right? I have this P1 and suddenly I have this, P1 and not P2 or P2. Okay, what's going on here? This is actually the distributive law, which is just like you remember from algebra. And I'm going to show it to you backwards. I'm going to show you how to go from here to this one, okay? And it's pretty straightforward. If you think about all that's happening here, we're just sort of factoring this in, right? We're distributing it in there. So if I take this P1 and this not P2, that's what I get here. Or this P1 and that P2 right there, which gives me what's right here. Okay, so I just did it backwards, but they're both valid. So now we're left with this final thing where P1, or not quite final thing, P1 and not P2 or P2. Okay, well, we know this must be true. It has to be true because not P2 or P2 will always be true, because if not P2 is true, then P2 is false, but if P2 is true, then not P2 is false, right? So no matter how you slice it, one of those will be true. They can't both be true or both be false. It has to be one of each, which means this whole thing evaluates to true. So that leads us to this formula right here, which is P1 and true. Okay, so we're going to learn more in depth. We're still not done here, but we're going to learn more in depth later, another day, another video, how all these rules, what they are called, and how you can use them. They're called logical equivalences. We'll get to them later, but that's what we've done. We've used these different logical equivalences to reduce this formula, reduce this equation, until we're down to this bullet point we're on at the moment, which says P1 and true. Well, there's one more logical equivalence that says when you have something and true, then the result of that will be whatever P1 happens to be. Okay? And if you think about that, that makes some sense. If P1 is true, well, what's true and true? That whole thing evaluates to true, right? So if P1 were true, then we have something that's true and something that's true, which means that whole thing is true. Okay? If P1 were false, however, you have a false and true. Well, what's that evaluate to? False, right? Well, in other words, it evaluates to whatever P1 is. So no matter which way you slice it, some proposition P ANDed with something that's definitely true evaluates to whatever P happens to be, right? So P1 and true are logically equivalent to P1. Okay, and again, we'll learn about that rule officially another day. But that is our final result, that P1. P1 is the only one that's true. Believe it or not, P1 is empty. Okay, so if P1 is, or excuse me, the treasure is in P1. So by the original rules of our proposition, P1 means the treasure is in trunk 1. And so that means it's here. So I know it's a long way to go to solve a silly riddle, but it gets the creative juices flowing. It helps you think more critically, helps you think logically, and solving logic problems, I cannot tell you how many times where this kind of thinking helped me crack some sort of really complicated logic statement in code, a mixture of ifs mixture of ands and ors in a big old long nasty if statement or something. This kind of thinking is critical. Okay, so hopefully that makes some sense, and then we can see why a logic puzzle can be very useful. Now, we've looked at a couple things today that take some formula or something, and we've applied some rules that we haven't officially learned about to reduce things down or to convert them into something that's propositionally logically equivalent. And it led us to a path. It helped us find the treasure here. It helped us know if Beavis could ride the roller coaster, maybe. It helped us see that there's more than one way to represent that. It helped us know if the specs were correct on a system, if they were actually satisfiable, or if they were consistent, right? Well, the next big thing that this can be very, very useful for is drawing propositional logic, or drawing logic circuits, right? So we're going to look at drawing logic circuits, and then later, another time, we're going to look at how to reduce that circuit using some of these propositional logic rules that we kind of touched on today. But for now, let's just see how we can convert either a circuit into a propositional equation or an equation into a circuit. So this guy, Claude Shannon, he's mentioned in the book. There's a little, one paragraph bio about him. Go look him up. Go read his papers and learn about him. This guy was brilliant. The sort of history of all this, right? We have George Boole, who figures out this idea that you can take propositional calculus from Aristotle and you can make these compound propositions, right? That's this whole P and Q and the conditional and all this stuff. That was George Boole that figured that out. Well, then Claude Shannon comes along in the 1940s or somewhere around there and has this idea, well, hey, I could take this George Boole stuff from about 100 years ago and I can actually use it to think through a logic circuit and apply it to logic circuits. Chapter 12 goes into this in great depth, how all this stuff can be applied to circuits. We're going to look at it on just a brief overview here, and maybe later touch on some of the chapter 12 stuff. But study that chapter in depth if you want. There's a lot of really cool stuff in there, and we're just going to sort of scratch the surface right now. So how does this work? Well, the first idea is this. We have what's called an AND gate, right? And now AND gates can have multiple inputs, and there are different types of gates. There are different types of circuits that have multiple outputs. We're just going to look at some super simple stuff today. But if I have an AND gate and I give it, for example, P as one of the inputs and Q as the other input, the output will be P and Q, right? Whatever that ends up being, right? If P is true and Q is false, or better said, 1 or 0, meaning voltage or not voltage, or high voltage, low voltage, right? It's never really on or off. It's high and low. But we think of that as true and false, right? If it's high, it's true. If it's false, it's low. And or if it's low, it's false. So we have P coming in and Q coming in. Well, whatever comes out is whatever P and Q is, right? An OR gate, which looks like this, it's just what you'd think. We have P and Q coming in, and whatever comes out is P or Q, whatever that evaluates to. And then we have the negation, the inverter. You can sometimes hear it called a NOT gate, but it's just an inverter, and it takes the signal and it turns it it just negates it. So if P is coming in, you get not P coming out. If not P was going in, well then not P comes out, right? Which is just P. Okay, so that's why it's called an inverter. So what can we do with this? Well, how about we can use it to determine the output of this combinatorial circuit, right? So here's the circuit. what's the final output going to be right here, right? Well, baby steps. First of all, we have P coming in here, and we have not Q right here, right? So let's just look at how this goes in one piece at a time. The bottom here, R becomes not R once it makes it through that inverter, right? Then after that, we have not Q coming out of this inverter, okay? And then at the top there, we have P coming in, and it comes out as P and not Q because those are the two inputs. What the actual values are, true, false, 1, 0, high, low, doesn't matter. It will be those two things ANDed together, right? So now the input to our OR gate is P and not Q, or not R, right? Which gives us that. So that is our final output of the circuit right there. And you can see clearly that's exactly what happened, right? The input to this OR gate was this right here, or this right here. Whatever that evaluates to, that will be the final output. Now, if you know what these initial values are, then you know what the output will be of that circuit. Now later, we're going to look at the idea of, if I have a circuit like this, can I take this equation right here and can I reduce it and make a better, more efficient circuit? We will look at how to do that another time, okay? But let's take a look at another example here. Let's go the other way. Can I build that circuit, right? That's the formula. How do I build that circuit, okay? So we start here. This is our final output. We're going to go backwards. That's our final output. Well, we know that the input was an AND gate, the input to this spot right here, okay? It was an AND gate. It was this and this, okay? So we get this, right? Well, we know what the input of that AND gate is. It's these two pieces of this output, right? So we then have those guys right there, right? I just took the parentheses off, but that's the same thing. Well, now if we look at those, you can see with each one, this is going to be an OR gate that preceded that, and this is also going to be an OR gate that preceded that. Okay, so let's see how that's going to play out. We have an OR gate there, and we know what the input to the OR gate was. It was that, and it was also that, right? Okay, so we have those two things. Well, again, we know what came before that. Another OR gate. We know what came before that, an inverter, right? So let's take a look at this. We have an OR gate that has as its input a Q, and it also has not R as its input, right? So we're done with Q. We've gotten all the way back to a single proposition or a single variable. And then the not R, of course, before that must have been an inverter. And then now we have the R. And then, of course, before that must have been an inverter. And we'll see that. That would be P. Okay, so we've gotten the bottom half of this right here. We figured out how we got to this input right here of that AND gate. It started with PQR. A couple of them went through inverters. Some of them went directly into the OR gate. We have our output here. That becomes the input there. We have this output that becomes that input, which gives us this whole messy thing here. Okay, so let's finish up the top portion of this. We know it's coming from an OR gate because we have P or not R, right? Well, we know what the input's going to be. It's going to be P, not R. And if we have a not R, well, where did it come from? It came from an inverter, which started with R. Now, when you get to stuff in Chapter 12 about Boolean algebra and all this stuff, the symbols change slightly. And typically you don't use P, Q, R, S. You use X, Y, Z, and so forth. But it's all pretty much the same thing. So this is yet another application of propositional logic that's very applicable to computer science and programming and hardware and all kinds of different things. So today, this was the plan, and we looked at all these different things, translating English into logic. We looked at system specifications and how we can make sure that the system actually is consistent and it actually works the way we're hoping it works. We looked at some logic puzzles, we did some practice exercises, And why do we care about all this stuff? Because making mathematical arguments or disambiguating the language or looking at hardware and software specs, it can be used in computer circuits. It can be used for writing code. We didn't really write any code today, but it can be used for writing and analyzing code. You can use it to solve logic problems, which can help with some of this other stuff. And you can use it to write a proof or to write code that writes a proof. So hopefully you can see that this stuff is not just fun stuff that you can do to, oh, let's just turn a sentence into math, right? Why would you want to do that? Hopefully this kind of clarifies some of that now and it makes a lot of sense. We're going to do a separate video that has a few practice exercises in it to help you be a little bit better prepared for your homework relating to this chapter. And that will be a little bit shorter video that you can just kind of walk through. There'll be pause points where you can look at it and walk through some of the problems. So hopefully this stuff is all kind of coming together and it makes sense why we care about it. See you all in the next video.